Welcome to Ask and Learn.
Problem, we are given the recurrence relation an is equal to 4 times an minus 1 minus 3 times an minus 2 plus 2 to the power of n plus n plus 3, where a naught is equal to 1 and a1 is equal to 4. So the first step is to find the roots characteristic equation, and so we're just going to take this recurrence relation and set an equal to r squared, an minus 1 equal to r, and an minus 2 equal to 1. And we're just going to treat the other functions of n to be 0. So that's going to be the last 3. And what we get then is r squared is equal to 4r minus 3. Okay, so we can solve this, right? We can rewrite it so that we get r squared minus 4r plus 3 is equal to 0. Then we just need to factor. And so when we factor this left-hand side, we get r minus 3 times r minus 1 being equal to 0. And so our roots then are going to be 1 and 3. So now we're going to use these roots to write our homogeneous linear recurrence relation. So the homogeneous portion, we'll put a little h at the top here for that, is going to be equal to alpha 1 times 1 to the power of n plus alpha 2 times 3 to the power of n. So this 1 and this 3 were our roots, and these alphas are going to be some sort of constant. And of course, 1 to the power of n is 1 no matter what. So this is really equal to alpha 1 plus alpha 2 times 3 to the power of n. Okay, so now we need to find the particular solution, right? Because our total solution is the homogeneous portion plus the particular portion. So to find the particular solution, we'll take f of n to be equal to, it's going to be equal to these remaining 3 portions that we initially ignored, right? So that's going to be equal to 2 to the power of n plus 3. Okay, but we can rewrite this. This is going to be the exact same as 2 to the power of n plus 3 times 1 to the power of n. Okay, and since 1 is a root and 2 is not a root, then we will write this as our particular portion. That's what the p is for. It's going to be equal to q times 2 to the power of n plus n times p1 times n plus p naught. Okay, and we can simplify that a little bit to be q times 2 to the power of n plus p1 times n squared plus p naught times n. And so now that we have this, we can go ahead and solve it because it needs to satisfy our recurrence relation. So what that's going to look like is we'll take our an is equal to the homogeneous and the particular portions, right? So we get that an is equal to 4 an minus 1 minus 3 times an minus 2 plus 2 to the power of n plus 3. And we'll put in our particular solution on the left-hand side because we know it needs to solve it. So then we get q times 2 to the power of n plus p1 times n squared plus p naught times n is equal to, and we can rewrite the right-hand side as well a little bit. So it's going to be equal to 4 times q times 2 to the power of n minus 1 plus 4 times p1 times n minus 1 squared plus 4 times p naught times n minus 1, right? So we really just put 4 times an minus 1, which would be 4 times this left-hand side, replacing all the n's with n minus 1. And now we're going to do the same for this next portion. So it's minus 3 times q times 2 to the n minus 2 minus 3 times p1 times n minus 2 squared minus 3 times p naught n minus 2. Okay, this is going to add 4 times 2 to the n minus 2. And in that case, we just took a 2 out. And we took 2 2's out, so that's where the 4 came from. And then we add n and add 3. So that's the fleshed out expression on the right-hand side. And so now if we move things around, we can add and subtract on the left-hand side from the right-hand side. We will get that 0 is equal to negative 4 q plus 8 q minus 3 q plus 4 times 2 to the n minus 2 plus p1 times negative n squared plus 4 times n minus 1 squared minus 3 times n minus 2 squared. And then we're going to add p naught times negative n plus 4 times n minus 1 minus 3 times n minus 2, and then plus n plus 3. Okay, and so that can be simplified. You can see a lot of these similar elements inside the brackets here. And so we simplify that, we end up with 0 being equal to q plus 4 times 2 to the power of n minus 2 plus p1 times 4n minus 8 plus 2 times p naught plus n plus 3. Okay, and that is equal to q plus 4, 2 times n minus 2, plus 4p1 plus n times n plus negative 8 P1 plus 2 P naught plus 3. So now we're sort of doing it in terms of n's, right? So we have to the power of n times n, no n involved. Okay, and we know that in this instance, the coefficients have to be 0 for this to equal 0. And so we get a system of equations. We get 0 must be equal to q plus 4. 0 must be equal to 4 times p1 plus 1, and it is also equal to negative 8 p1 plus 2 times p naught plus 3. Well, this first equation is quite simple. This gives us that q is equal to negative 4. The second one is also pretty simple. This gives us p1 is equal to negative 1/4, right? We subtract the 1 and divide by 4. And then we can put this value of p1 into the second equation to get this to be equal to 2 plus 2p naught plus 3. Right, so this means we would subtract 5. So we get negative 5 is equal to 2p naught. So that means that p naught must be equal to negative 5/2. So now that we have these, we can write our particular solution. So we have that our particular solution is equal to, which was equal to q times 2 to the power of n plus p1 times n squared plus p naught times n becomes negative 4 times 2 to the power of n minus 1/4 n squared minus 5/2 times n. And so to solve the whole thing, we'll take our homogeneous portion and add it to our particular solution. And so that gives us alpha 1 plus alpha 2 times 3 to the power of n minus 4 times 2 to the power of n minus 1/4 n squared minus 5/2 of n. And we're not quite done yet because we need to evaluate at the initial conditions, right? So what we know then is that 1 is going to be equal to, which is our a naught. So that's going to be equal to alpha 1 plus alpha 2 minus 4. And then when we evaluated at 1, we got 4. So that means that alpha 1 plus 3 times alpha 2 minus 8 minus 1/4 minus 5/2 is equal to 4. So we're going to combine the like terms. And so this turns into 5 is equal to alpha 1 plus alpha 2. And 59/4, that's a bit of an ugly fraction, but that will be equal to alpha 1 plus 3 times alpha 2. So we can subtract the two equations. And we will end up with 39/8 is equal to alpha 2. And now that we know alpha 2, we can just kind of pop it into that first equation. right? So we would get 5 minus 39/8 is equal to alpha 1. And that is equal to 1/8. Okay, so now that we know everything, we can, we have alpha 1 and alpha 2. We can just go back here and put them into their respective places. So this is going to be that AN is equal to 1/8 plus 39/8 times 3 to the power of n minus 4 times 2 to the power of n minus 1/4 times n squared minus 5/2 times n.